Welcome back to the course Modeling Combustion with Answers Fluent offered by ADA Systems. In today's class, we will discuss about premixed combustion model. So let's begin the class. So what is premixed combustion model? So we have seen earlier the non-premixed combustion model, and compared to it, premixed combustion modeling is very much difficult and complex because the premixed combustion occurs as a thin propagating flame that is stretched and controlled by turbulence. So turbulence is the thing which controls the combustion and propagation of premixed flames, and so the essence of modeling this kind of combustion lies in capturing the turbulent flame speed. So the main focus for this premixed combustion model is to simulate and to understand the laminar flame speed as well as the turbulent flame speed. So just like non-premixed combustion model, here in this model, one of the important parameter which holds the entire thermochemistry is the progress variable. In non-premixed combustion model, it was the mixture fraction. Here it is the progress variable. But both of these factors are very different from each other. So wherever C equals to 0, that means that unburned gases are present there, and wherever C equals to 1, that means burnt gases are present there. So the flame which occurs in premixed combustion is in the range of C equals to 0 to C equals to 1. So this helps in visualizing and putting our boundary conditions very specifically so that a premixed combustion model can be simulated. So some of the key features of this model are: this model offers two types of flame speed determination models, that is Zimot flame speed model and Peters flame speed model. So for this model to ignite the premixed mixture which is present, we can use the spark ignition model. Then one more thing which is important in modeling premixed combustion is that here we have to specify each and every unburnt physical property for the unburnt mixture. So unburnt density and unburnt temperature are some of the properties. Other properties we will see in detail in upcoming slides. Then we discussed about defining the progress variable C, and the last one, that these models have three options, that either we can model our premixed combustion using C equation, G equation and extended coherent flame model. So these three models are different, but overall the aim or the motto to model premixed combustion is the same. So some of the limitations for this model are: this model does not work with density based solver. Also pollutant models cannot be used with this model, and then this model can be used only to model deflagration flames, that is subsonic flame. We cannot model detonation using premixed combustion model. So this was complete overview for premixed combustion model. Now we will see what all are the steps involved in modeling premixed combustion. So these are the steps which will help us model a premixed problem using Answers Fluent in a very better way. So we'll discuss each of the steps progressively in upcoming slides. So coming to the first step, that is enabling the premixed turbulent combustion model and its related parameters. So after defining the turbulence model and energy model, we have to come into species and we have to enable the premixed combustion model, where we can select what energy treatment we want to use, just like the other models, that is adiabatic or non-adiabatic. Then we can select what premixed model we want to use, that is C equation, G equation or extended coherent flame model. So based on whatever we select, we can change our turbulent flame speed model from Zimot to Peters. So when we select this Peters flame speed model, we are able to modify the model constants or some of the main parameters which defines the Peters flame speed model. So this option is only available for Peters flame speed model. So next, for the second step, it is defining the physical properties of the unburnt materials in the domain. So after defining the models and everything, we have to specify the unburnt physical properties like laminar flame speed, critical rate of strain, etc. So when we are selecting adiabatic or non-adiabatic, these set of parameters will change accordingly. We have to specify these parameters based on the standard conditions. To get these values of properties, we can refer to some standard combustion handbooks. So the next third step here is setting the value of progress variable at our flow inlets and exits. So as we have seen that there will be a flame propagating. So wherever C equals to 0, that means an unburnt mixture, that is where the pre-mixed air and fuel mixture is present at inlets. So we will define C equals to 0 at inlets and C equals to 1 at our exit, so that a flame is propagated into this range from inlet to outlet. So the next step, the fourth step, is initializing the value of progress variable. So even after giving some boundary conditions of C equals to 0 and C equals to 1, it may happen sometimes based on the problem that the flame may blow back into the stabilizer. So a very good practice here is to patch the progress variable based problem. That is, upstream we will patch C equals to 0 and downstream we will patch the progress variable as C equals to 1. So this may reduce any blowing back of the flame problem when modeling premixed combustion. So this can be done into solution initialization, and there we have an option of patching. So after patching the value of progress variable, then we have to start our simulation, and then we have to perform post processing. So even here there might be some convergence issues. So same strategies which we have used for earlier two models, we can use the same strategies to make our solution convergent, that is by changing some of the under relaxation factors, performing a cold flow simulation earlier and then hot flow. So the post processing parameters which we can use for premixed combustion model are shown below. So we can generate graphical plots or alphanumeric reports of the following terms when we are done with premixed combustion model. So what are the things we studied in today's class? The summary for the class is that we've seen premixed combustion modeling is difficult than modeling non-premixed combustion model because the flame occurs as a thin propagating flame which is controlled by turbulence, and thus making this as the motto or the focus of the model that it has to simulate the laminar flame speed as well as the turbulent flame speed. Then we have seen that progress variable is the parameter which holds the entire thermochemistry of the model and helps in defining the burnt and unburnt mixture in the domain. So this model offers two flame speed models, that is Zimot and Peters flame speed model. So based on what condition we are dealing with, we can select a turbulent flame speed model. Then we have seen that we can use spark ignition model along with premixed combustion model to ignite the premixed mixture which is present at our inlets. Then we have seen some of the disadvantages of the model, that pollutant models cannot be used along with it when it does not work with density based solver, and only deflagration flames can be modeled using premixed combustion. Then at last we have seen all the steps which are useful in modeling premixed combustion in detail. So these are the references for today's class. So in next class we will start with partially premixed combustion model. Thank you.